For the last step here, we're going to plot the manipulated data, and that's going to be our test to see if this, our position, is really related to time squared. Basically, to find the answer to that, if you get a straight diagonal line, we know that position is related to time squared. If you do not, we have to go, you guessed wrong essentially with what function it was, and you have to go back and figure out, retest a different function. So we're going to take our data, position versus time squared, and we are going to plot it again in a scatter plot. So we're going to go to chart, we're going to go to insert. Okay, and if we look at this, we can see our data pretty much makes a straight diagonal line. Okay, now in order to come up with the equation and analyze the equation, instead of printing this and manually calculating the slope, we are going to use modern technology. So for this part, please pay attention. You're going to come over here to customize and click on customize. You're going to go down to series. And when you click on series, all right, you're going to scroll down and find where it says trend line. Click on trend line. It will show you the trend line for your data. Okay, and then you are going to continue to scroll down. So there's our trend line. You're going to go to label, you're going to go use equation, and it's going to give you the equation. And then you're going to click on something called the R-squared value, which is a statistical term that if it is linear, it should be, if the data is actually a good fit. So in other words, if the position is really a function of time squared, the R-squared value should be 0.9 or higher. Okay. In this case, it's 0.998, so it is a very good fit. So we can say with confidence that position for a ball falling and accelerating at a constant acceleration is directly proportional to time squared. So now to actually get the equation, this is not the last step. The last step is to write this out, because when we look at this, so this is our y equals mx plus b value. The r squared is a separate term. On our y-axis, we have position. So position will be equal to 5.77, which is the slope. And the units would be meters divided by seconds squared, multiplied by time squared. Oops, not quite done yet. Plus 0.0363 meters. So a couple of things here. One, it's not just going to be time, because we actually squared time in this case and plotted position versus time squared. So we're looking at not a position versus time graph, but a position versus time squared graph. Two, you have to pay attention to your unit. So in this case, our initial position would have been, we look at, when we flip the reference frame, would have been 0. So this 0.0363 meters is really, really close to 0. So that makes a lot of sense. The slope was half the value of the acceleration, which is roughly 5.77. We'll discuss that a little bit later and what that means, or what that ultimately means. But for now, all I'm concerned with is your ability to plot the original data, manipulate it, plot the manipulated data, and come up with the equation. So that is what you're going to be working on. There are 4 data sets at the bottom of this. You're going to plot them, you're going to manipulate them, and you're going to find the equation for the original data in each one using the process that I had just outlined.